we all pull together and really work on things, use the best of what's out there, the outcome can be really spectacular.
I grew up watching Star Trek with my grandfather, believe it or not. And he was always pretty enamored at the idea of going out and exploring. And
I was, I think, 6 or 7 years old, and I was with my grandparents, and we were looking at the TV. It was the first flight of Ariane. This is really the beginning of the story for me.
When I was in college, I got into a student group that was building rockets. I got to do hands-on projects and actually build things, and I really fell in love with it.
One of the things that makes me really love being part of this industry is how often things seem impossible and then someone does them. And so when I think about like what I could do with my skill set, my time on the planet, I always thought it would be a good idea to expand the resources available to us.
space is where the infinite resources are. There's only so much stuff on Earth. And I don't care how much we conserve, there's only so much of it.
That sense of wonder, combined with relentless determination, is fueling a new space age. Driven by daunting challenges here on Earth, from limited resources to the vast digital divide.
Internet access is a thing that we take for granted all the time. It's in our pockets, it's on our laptops. I didn't take it for granted. I thought it was incredibly important. I think it's a huge injustice that there are people who don't have access to the internet today. Whatever your thing is that you're passionate about, all those problems get solved faster, better, if more people in the world are contributing to them. And right now, there's just a huge pool of talent that's not able to contribute. So in my mind, this was the biggest kind of force multiplier on my time. If I can solve this problem, then all the other problems get solved as well.
Space innovation has helped people on the ground time and time again. If you were trapped out in the middle of nowhere and you were lost in your car, what do? You pull up your phone and it can locate you using GPS. Like, how scary would it be to have a world where GPS just stopped existing? Like, you would be lost much more often, you would travel less. GPS comes from space, it comes from satellites that are up there. There's 31 satellites and they provide GPS for the military, but then also for your phone to help you not be lost. So that's where satellite comes in. Satellite is the way that you connect people anywhere on Earth, no matter where they are. We want to build 100 satellites by 2030.
Right now there is a huge demand to get satellites and spacecraft up off the ground and into space, but as a planet we do not have enough rockets to get them there. So many spacecraft end up waiting years for their chance to launch. We're really hoping that we can help meet that demand to support all of these great projects that need to get up into space. I am a propulsion design and analysis engineer here at Relativity Space, and our propulsion team is focused on developing the AON-R engine, which is a liquid fuel engine that generates over 250,000 pounds of thrust.
3, 2, 1.
Humanity has spent a little bit of time in space so far, and we've done pretty amazing things. We have GPS now. We have the ability to talk to people anywhere in the world from where we are. You can even use the internet from space now, and more things are coming. I think that's really just the start. So I'm at Relativity. I've worked in this industry for a while to continue to see what else we can do. We launched our first rocket, Terran 1, back in March of 2023, and we definitely met our objectives, even if we didn't get all the way to space. And at this time, we were pivoting to a much larger reusable vehicle called Terran-R. And that involves a lot of reliance on simulation, a little bit of experience, and we put that together to try and have the best debut launch for Terran-R that we can, and then quickly ramp to a lot of customer launches thereafter.
Across the Atlantic, European pioneers are also developing next-generation launchers, focusing on reusable technology, environmental sustainability, and servicing the growing space economy directly linked to life here on Earth.
I remember that when I was a young student, some of my teachers, and female teachers, told me, no, but engineering is not for female. Do something else. And clearly, I fight against this, and I succeed in having my degree in engineering and doing what I want to work in space. So really believe in your dream, don't be shy, and don't be afraid. Maya launcher is a two-stage to-orbit launcher, which has a very innovative technology, which is to reuse the first stage. So it lands on a barge on the sea, using landing legs, grid fields, aerodynamical devices that allow to reach this barge on the sea. It uses methane and oxygen propulsion, which allows to have a very efficient reusable stage with capability to reignite the engine in a proper way. The objective of this new propulsion for us is to limit its environmental impact around one purpose, one objective, which is to develop the best launch service we can.
I don't know how you came there to our facility this morning, probably with GPS helping you. This is a spacecraft and this is very useful. This is what we are dealing with. We are focusing on launching spacecraft that are really bound to the Earth's economy and that have a meaningful impact on Earth. The biggest part of the space activity is about collecting data, sending signals that are used in the real Earth economy. It's not space for itself, it's not exploration, which is incredible. But the biggest part of the space activity is about collecting picture, video, signal, infrared signal, monitoring the resources on Earth. You know, resources, we have water and depletion of some of these resources that we need to live as human beings on Earth. And all of this can be monitored from space.
You know, is space expensive? Yeah, it is. It really is. Is space hard? Yes, space is hard. It is unforgiving. You know, it will destroy technology, it will destroy machines, and it will kill people in a heartbeat. We need to learn how to do that. It is hard because the rewards are that big.
Beyond Earth's atmosphere, Intuitive Machines is leading the charge back to the Moon, aiming to create sustainable lunar access for science, exploration, and the potential utilization of off-world resources.
Intuitive Machines is a diversified space company focusing on cislunar, but then looking beyond, looking at LEO, looking anywhere that people might want to go into space and enabling that and bringing everyone along with us. With IM-1, we changed the economics of landing on the moon. We landed 100 kilograms on the moon. We proved you can do it. That was insane. There's a couple things that are pretty exciting. We're going to land really close to the South Pole on a little ridge at the peak of Malapert Mountain. Super challenging. If you think fly down and land on that ridge in the Himalayas at the peak of Everest, right? That little thing we all see on the pictures, that's sort of that last hike everybody does, that's where we're landing. The far side of that, you fall down into a deep, dark crater. The near side, you fall into a lit crater, but you still fall into a crater. So we're coming on that little bridge. So navigation's a real trick. But when we land, we're looking for resources. We're looking for frozen water. We're looking for volatiles. With IM-1, every hour we got on the moon was data, was pictures, was science. We were racing literally against the clock. When the sun set, we lost our power, and that was it, mission over. But every hour of time we had the radios up, and we were pulling science down, is science. And if I can spend that on those batteries, bring down more science, as opposed to I've got to put it into a heater that I didn't know about, or a radio just to burn that margin, I mean, you never get that time back. And that's the most valuable thing for us.
For companies like Astranis, bridging the digital divide isn't just about building satellites. It's about transforming lives in tangible ways.
I've had the chance to meet a lot of people that will use our satellites in the future. I've flown to Mexico, flown to the Philippines, and in Mexico, I saw firsthand the impact that connectivity can have, not only in the ways that you expect, but also in very unexpected ways. So the way you expect is people are connected. They can go browse the internet, they can do things with it, like learn things. So you connect to school. What happens when you connect to school? The kids can learn. That's the obvious one. But the non-obvious one is what you actually learn by going there, which is because the school is connected, parents are coming and hanging out at the school when they're like picking up their kids and before and after. It's just like a local place where people in the town gather. But not only that, now that we have a local gathering place in town, there's all these vendors that come and start to serve those people. So we're generating economic activity in addition to the community, in addition to the connection for education. So there's all these second and third order effects that come from people being connected, and I saw that firsthand when I was in Mexico. Astranis builds small satellites for geostationary orbit. You traditionally see a lot of satellites operating within what are called the Van Allen belts, which is basically because the Earth is a rotating ball of metal on the inside, it creates a magnetic field. The magnetic field traps radiation and prevents us on the ground from getting fried by the sun, basically. But what it also protects is the low Earth orbit orbits. So it protects the International Space Station, it protects all those satellites that are, the vast majority of satellites that are on orbit today. But we don't have that luxury. So we are further than that. We are out beyond the Van Allen belts. We're actually in the very outside of the outer Van Allen belt. That means that we see a lot of radiation that's coming from deep space that's also trapped in the belt itself.
If people don't know, LEO is about 500 miles above the Earth's surface, and GEO is 22,000 miles. So we're talking, 40 times as far away. It's a lot harder to get there. You need a lot more fuel. Fuel means size, means mass. The other big difference is that in GEO, you're exposed to the very harsh space environment. So you're being pelted with all sorts of radiation that in LEO, the atmosphere is protecting you from. So designing your electronics in a way that they can sustain that. And that's really difficult. And for those reasons, a lot of people have just chosen to build in LEO. The downside of LEO is that one satellite cannot do the job. You need constellations of thousands, sometimes tens of thousands of satellites in order to be able to begin service. In GEO, a satellite is parked overhead, so you want to serve a place on Earth, you want to bring them internet, great, build one satellite, put it up, and you're set. In many ways, we will succeed or fail depending on if we find great partners to work with. If we have great partners, those partners bolster us and make us able to achieve our mission. So very early on, we realized partnerships were going to be incredibly, incredibly important to us, especially because we were so small and there was so much to do. And we set out to go find those great partners, and Ansys was a natural fit for us.
Deep tech is expensive. It's hard to build a lot of hardware. I mean, that's the benefit of having simulation software, is that you can use it to simulate things instead of building them. Because when we launch satellites, we only get one try. Like, we're not gonna, send up a satellite and then hope it works and then figure it out and try to debug it on the fly and set up an astronaut or something. Too expensive. So instead what we do is we build really, really detailed sims on the ground and test those like crazy before we send satellites into orbit. And they actually call this hardware in the loop testing. You'll hear it referred to as HITL testing, H-I-T-L, lots of acronyms in space, we love them. And what that means is you first build the thing in software, and then you replace bit by bit in hardware as you kind of go along through different layers of fidelity. It saves costs, it saves us lots of time, and really it just means that we're able to build things that probably would be impossible if we couldn't simulate it all.
Simulation for us is a force multiplier. It lets us try different ideas, right? And try them in a computer simulation or in a model, and try a bunch of different ideas very quickly. And what that lets us do is have those whiteboard sessions and be creative and think about different ways to solve a problem, different ways to address something.
To be able to test things that we wouldn't be able to test if we have to have all the things physically brought into the factory. So sometimes we just want to try something that we think could work, and simulation can help us decide. We need flexibility and be able to adapt to design changes that are quite frequent. And I think it's especially true as a thermal engineer, because we are often subject to the design changes that are in different domains, like mechanical changes or propulsion changes. So it is important as a thermal engineer to be able to react quickly and to adapt our model to this change. I build simulation models and perform thermal calculation in order to anticipate future problems and to make sure that all the temperatures are good.
Rocket engines experience very extreme environments, and so in order to design parts to withstand that, we need to do extensive simulation and testing to make sure that our parts can hold up to those loads and also be as lightweight as possible, because weight is super important when you're sending things into space. The more things that we can test virtually through a simulation means the fewer things we need to test physically, and physical testing is incredibly expensive, especially for a rocket engine. So simulation allows me to iterate through dozens of different design possibilities to narrow them down before a part even gets created. This allows me to have really high confidence in the parts that I'm putting onto the engine before they're even manufactured. Last year, we tested the ANR engine for the very first time, and within a week of putting that engine onto our test stand, we were able to achieve a full mission duration hot fire. That basically means that everything had to work perfectly the first time. This is a pretty unprecedented pace. It's something that I am the most proud of our propulsion team here at Relativity, and it would not have been possible without great simulation during our design phase.
That early phase of design is really interesting, where you're brainstorming, you're trying to think, how can we do this in a way that we couldn't do before? And so I'm always looking at what new capabilities can we extract, how can these simulation tools help us improve the products that we're building.
We're trying to go faster and cheaper to that same level of performance with the product with Terranar. And that means we have to take a different approach. So this is where simulation comes in for us, because we are trying to do only a couple iterations at the top level of the vehicle and use a lot more simulation up front to make sure the first one we fly is really close to that final product. At the top level, we use simulation to really identify what matters overall for these systems. There are top-level system simulations that some teams build here at Relativity just to figure out between all the different parts of the manufacturing stack on the additive side or in the entire launch system, what things really matter. And then from there, we try to optimize by making individual parts better and better that are really impactful overall. And that's where individual simulations for things like structures, propulsion, avionics, even software come into play. It's using a little bit of experience and modern tools, and Ansys plays a big role in that, in going fast where we really need to in simulation, and then just learning other things at full scale.
On the day we actually launched it, there was like so much anticipation. You're building up, you're imagining what life will be like after it happens. There was a period of time where I was sitting there, I was just like standing there, the rocket is sitting far in the distance, it's huge and like big, badass and scary. Hear the countdown, 5, 4, 3, 2, 1. But it's silent. That's the craziest thing, because it's so far away, for safety reasons obviously, but it's so far away that you see it like way before it actually, you hear it and feel it. Like it's just a little speck, and it grows up startlingly fast and like shoots into the sky really fast. And then 30 seconds later, you see these like ripples, like Jurassic Park style, coming across the water. And then woof, it just like hits you with this wall of sound. Crazy experience. We and then it's like so gone. It's gone so fast. It's gone in like a minute. It goes off into the distance, like way far out, and then you're like barely looking. You're like, is that still it? Or like, or can we still see it? And then you see the second stage light up, and it just like takes off, and that you can see really clearly too. And then you wait for 4.5 hours. We like literally, so it takes a long time to get out to where we're going. And so first satellite pops off perfectly right in the right spot. Second satellite pops off perfectly right in the right spot. And then we're the third and final satellite, the final part of the mission. And so we're just sitting there waiting. And then finally it's like, and our satellite just floats off into the distance, and its separation was nominal, everything's perfect. But then we just like heard from it immediately. Like there was no wait. I expected to wait another 30 minutes, hour to hear from the satellite, but we just immediately heard from it, and it worked. And its solar arrays were already deployed, crazily enough. We got a video from the viewpoint of the second stage that saw the solar arrays open. So it's like it starts off and Arcturus is a little cube, then it just goes and like grows into a rectangle. It's like super cool. So it was an amazing day. It was so cool to see all that happen.
So by the time the launch actually happened, there had been all this buildup and anticipation, and that feeling of release was so massive. I also had just had a baby. I literally have a baby in a carrier, and there was something really magical about being like, I'm here with my baby, and it was our first satellite we built, and I don't know, something about that just felt really magical to me personally.
So it's very exciting also for me to have seen what it was before, to see the change coming. Now it's a time for a change. It's one time in your working lifetime, so you better catch it and make have fun with that. And this is what I did.
As we look beyond the satellite market, I think there are other opportunities out there. Some things that folks are working on right now are private space stations, having medical labs in outer space, or even potentially flying private missions to Mars or the Moon, which we're actually already contracted to do with Impulse Space.
If I can make my own oxygen, if I can melt the ice and I've got water, right? With something like a Methalox engine, I need methane and oxygen, and I've got rocket fuel. Those things I can find out there in the solar system. Maybe I can find them on the Moon. And so now I've got resources. Now I can sustain a base. Now I can keep people alive. Now I can refuel my vehicles, and I can refuel my rockets. You know, Earth is tiny. It's a speck of sand. If we can get access to what's out there, if we can learn to live out there,
you.